This is SpaceTime, Series 27, Episode 103, for broadcast on the 26th of August 2024. Coming up on SpaceTime, NASA decides to return the stranded Starliner crew to Earth aboard rival SpaceX's Dragon. Tracking down the asteroid that killed the dinosaurs, the JUICE spacecraft completes the first ever joint lunar-Earth gravity assist flyby, and 3 more Australian satellites sent into orbit. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
NASA has decided to return the stranded Starliner crew to Earth aboard rival SpaceX's Dragon capsule. The move follows ongoing concerns about the reliability of the Starliner spacecraft they flew up on. The decision means Butch Wiltmore and Sonny Williams' planned 8-day test flight to the International Space Station will now stretch out to some 8 months, the pair not returning to Earth until February next year. NASA's now instructed Boeing to return the Starliner to Earth without astronauts on board so they can continue gathering test data on the spacecraft during its flight home. Wiltmore and Williams will now formally become part of the Expedition 7172 crew through to February 2025. They'll then fly back to Earth aboard a Dragon spacecraft, with 2 other crew members assigned to the agency's SpaceX Crew 9 mission. Starliner is expected to depart the space station and make a controlled autonomous re-entry and landing at the White Sands Missile Range in New Mexico sometime next month. The problems with Starliner are quite extensive, but mostly centre around ongoing helium leaks in the service module and issues which cause the sudden shutdown of reaction control system thrusters. They're used to manoeuvre the spacecraft, especially during the crucial approach and docking to the space station. The docking, which was supposed to be carried out automatically, instead needed to be carried out manually because of the ongoing thruster problems. Since then, engineering teams have completed a significant amount of work, including reviewing a collection of data, conducting flight and ground testing, hosting independent reviews with agency propulsion experts, and developing various return contingency plans. However, the ongoing uncertainty and the lack of expert agreement between Boeing and NASA has forced NASA to make the decision to cascade the Boeing crew onto the SpaceX Crew 9 mission. Starliner is designed to operate autonomously and previously completed 2 unmanned orbital test flights, the first of which almost ended in disaster following a series of major computer issues. These firstly put Starliner into the wrong orbit, preventing it from docking with the space station. A second computer issue meant that even if they had reached the orbiting outpost, they still would not have been able to dock. But the biggest problem was the third computer issue. That would have caused the command module to collide with the service module as it was being jettisoned prior to re-entry. NASA and Boeing are now developing a new end-of-mission flight plan and set up Starliner systems for the unmanned return flight in coming weeks. Starliner needs to return to Earth before the Dragon Crew 9 mission launches in order to ensure a docking port will be available on the station. Following Starliner's return to Earth, NASA will review all mission-related data to determine what additional actions need to be taken in order to meet NASA's future certification requirements. The agency's SpaceX Crew 9 mission, originally slated for 4 crew members, will launch no earlier than Tuesday, September the 24th. NASA and SpaceX are currently working on several items before launch, including reconfiguring the seating on the Crew 9 Dragon and adjusting the manifest to carry additional cargo, personal effects, and Dragon-specific spacesuits for Wiltmore and Williams. In addition, NASA and SpaceX will now use the new facilities at Space Launch Complex 40 at Cape Canaveral to launch Crew 9. It provides increased operational flexibility around NASA's planned Europa Clipper launch. The Crew 9 mission will be the 9th rotational mission for SpaceX under NASA's Commercial Crew Program to transport astronauts to and from the International Space Station. This is SpaceTime. Still to come, tracking down the asteroid that killed the dinosaurs, the JUICE spacecraft completes the first ever joint lunar-Earth gravity assist flyby, and 3 more Australian satellites sent into orbit. All that and more still to come on SpaceTime. A new study claims the asteroid which triggered the extinction of 75% of all life on Earth, including all the non-avian dinosaurs 66 million years ago, originated beyond the orbit of Jupiter during the early development of the solar system. The findings, reported in the journal Science, are based on a new analysis of the KT boundary layer, a global geological feature composed of ash and debris from the asteroid impact event containing unusually high levels of iridium, a metal rare on Earth but common in asteroids. The impact, which triggered the planet's fifth mass extinction event, was caused by a 10 to 15 kilometre wide asteroid slamming into a shallow sea off the coast of what now is the Gulf of Mexico's Yucatan Peninsula. That collision released as much energy as 100 teratons of TNT. To put that another way, that's 1 billion times more power than the Hiroshima and Nagasaki atomic bombs used to end the Second World War. The initial impact created the 180-kilometre wide Chicxulub crater, throwing molten ejecta and debris high into the atmosphere and triggering a massive tsunami hundreds of metres high, together with devastating earthquakes, volcanic eruptions and even land tsunamis, all of which combined to shake the entire planet. In fact, shockwaves from the collision circled the Earth several times. Burning debris from the impact ejecta eventually began raining back down onto the surface, causing an intense pulse of infrared radiation, which began cooking any life exposed to it, and when combined with the molten lava flowing from all those volcanic eruptions, sparked global wildfires which devastated vast areas, burning out vegetation and killing any animal life that managed to survive the initial blast wave. Making matters even worse, the asteroid impacted the planet at a location rich in sulfate-containing gypsum, which was instantly vaporized and then dispersed as an aerosol into the atmosphere, only to fall back down onto the surface as highly caustic acid rain, burning anything it touched and causing long-term effects to the environment, climate and food chain. Smoke and ash from the wildfires and volcanic eruptions, together with dust from the ejected debris, initially created a blanket-like greenhouse effect, preventing heat from escaping the planet and causing the Earth's surface temperatures to soar. Now, eventually those temperatures cooled, as the smoke, ash, dust and ejected debris blocked out the sunlight for months, if not years on end, creating an impact winter, causing temperatures to plummet. Now, at around the same time as all this was happening, massive volcanic eruptions in what is now India, known as the Deccan Traps flood basalts, began flowing across the subcontinent. That pumped out even more toxic gas and pollution to the atmosphere, further contributing to the growing impact winter. Now, scientists have been examining the KT boundary layer, looking at its high concentrations of platinum group metals, which came from the asteroid and are extremely rare in the Earth's crust. By analysing the isotopic composition of the platinum metal ruthenium, the authors discovered that the asteroid's composition is consistent with that of carbonaceous meteorites. These originally formed beyond the orbit of Jupiter during the solar system's formation 4.6 billion years ago. The study's lead author, Mario Fischer-Gotti from the University of Cologne, says the impact of an asteroid like the one at Chicxulub's a very rare and unique event in geological time. The authors also looked at ruthenium isotope compositions from other craters and impact structures of different ages on Earth for comparison. And that data was surprising. It shows that within the last 500 million years, almost exclusively fragments of S-type asteroids have been hitting the Earth. In contrast to the impact of the KT boundary event asteroid 66 million years ago, these other asteroids usually tend to originate from the inner solar system, as do well over 80% of all asteroid impacts on Earth, making the Chicxulub event rare and unique in geological time. This is SpaceTime. Still to come, Europe's JUICE spacecraft completes the first ever joint lunar-Earth gravity assist flyby. And 3 more Australian satellites sent into orbit. All that and more still to come on SpaceTime. The European Space Agency's JUICE, Jupiter Icy Moons Explorer spacecraft, has successfully completed the first ever joint lunar-Earth gravity assist flyby, flinging itself just as planned towards the planet Venus. The Venus excursion will be another gravity assist flyby, all part of a celestial dance designed to accelerate JUICE towards its ultimate target, Jupiter, and its icy Galilean moons. During its lunar flyby, JUICE captured some stunning new images of the moon with its monitoring cameras. The images are showing signs of real colour differences in large-scale features on the lunar surface. All the more impressive because the monitoring cameras were designed to monitor the spacecraft's various booms and antennas, especially during the challenging deployment period following launch. They weren't designed to carry out science or image the moon. For that, there's a purpose-built scientific camera called Janus. It's providing high-resolution imagery during the cruise phase, as well as the flybys of the Earth, the Moon and Venus, and of course of Jupiter and its icy moons once the spacecraft is in the Jovian system. The close gravity-assist flyby approach to the Moon was designed to guide JUICE towards a similar close approach with the Earth just 24 hours later. And just as with the Moon, as JUICE flew just 6,840 kilometres above Southeast Asia and the Pacific Ocean, it snapped a series of images with its onboard monitoring cameras and collected scientific data with 8 of its 10 instruments. ESA mission managers say the gravity-assist flybys of the Moon and Earth were flawless. The flyby of the Moon increased JUICE's speed by 0.9 kilometres per second relative to the Sun, guiding JUICE towards the Earth. Then the flyby of the Earth just a day later reduced JUICE's speed by 4.8 kilometres per second relative to the Sun, but also guided JUICE on a new trajectory towards Venus. Overall, the lunar-Earth flybys deflected JUICE by an angle of around 100 degrees compared to its pre-flyby path. These inherently risky flyby manoeuvres require ultra-precise real-time navigation, but at the same time, it's saving the mission around 100 to 150 kilograms of propellant. Over the past month, mission managers gave JUICE a series of slight nudges in order to put it on exactly the right approach trajectory. And thanks to a flawless Ariane 5 launch from Kourou back in April last year, JUICE already had a little extra propellant left in its tanks to get closer to Jupiter's big moon Ganymede than originally planned. The success of the lunar-Earth flyby has now safeguarded this bonus science. Whilst the main goal was to alter JUICE's trajectory, the lunar-Earth flyby also provided an opportunity to test out JUICE's scientific instruments in space, with all 10 switched on during the Moon flyby and 8 switched on during the Earth close encounter. JUICE's next encounter will be with Venus in August 2025, and that Venus flyby will boost JUICE back towards the Earth for yet another flyby. The spacecraft will zoom past our home planet again in September 2026 and then again in January 2029, in the process gaining 2 more gravity assist boosts before finally arriving in the Jovian system in July 2031. The European Space Agency-led mission also includes technology from NASA, JAXA and the Israeli Space Agency. JUICE will undertake detailed observations of the gas giant Jupiter, as well as its 3 largest subsurface ocean-bearing moons, Ganymede, Callisto and Europa. The mission will characterise these moons using a powerful suite of remote sensing, geophysical and in-situ instruments to discover more about these bodies and help determine their habitability for past or maybe even present life. JUICE will also monitor Jupiter's complex magnetic, radiation and plasma environment and its interplay with the moons, studying the Jovian system as an archetype for gas giant systems across the universe. JUICE will make 35 flybys of the 3 large moons while orbiting Jupiter, before finally settling down into a permanent orbit around Ganymede. This report from ESA TV.
Last year, our Jupiter Icy Moons Explorer, also known as JUICE, set off on its 8-year journey to Jupiter. JUICE is on its way to study Jupiter and its 3 largest moons, Callisto, Europa and Ganymede. The mission will investigate these moons' potential to support life by examining their subsurface oceans. JUICE is expected to arrive at Jupiter in July 2031, 8 years after launch, after a series of flybys of Earth, Venus and the Earth-Moon system, the first manoeuvre of its kind. But why is the journey so long? At their closest point, Earth and Jupiter are separated by almost 600 million kilometres. JUICE has already travelled over 1,000 million kilometres, yet it's only 15% of the way there. The answer depends on a variety of factors that our flight dynamic experts know well, from the amount of fuel used to the power of the rocket, mass of a spacecraft and geometry of the planets. What are the challenges to get to Jupiter? 1. The Earth is moving. On the surface of Earth, typically the fastest way to travel somewhere is the straightest possible line. However, in space, straight lines are a massive waste of energy. When we look up at the night sky and track the motions of planets, moons, stars and galaxies, you'll see they're always in motion around another object. When we launch a rocket, it doesn't leap from a still Earth, but from a planet zooming at about 30 kilometers per second around the Sun. As such, a spacecraft launched from Earth already has a great deal of orbital energy, the only unit that matters when determining the size of an orbit around a central body. Just after launch, a spacecraft is in more or less the same orbit as our planet is around the Sun. To break free from this orbit and fly in the shortest possible straight line from Earth to Jupiter would need a big rocket and a lot of fuel. It can be done, but the problem is you'd then need even more fuel to break and go into orbit around Jupiter and not be flung past it. 2. Jupiter and Earth are both moving and not on the same route. Jupiter and Earth are always moving with respect to each other. This means at their furthest distance, when they are on opposite sides of the Sun, they are separated by whopping 968 million kilometres. The shortest distance between them is just under 600 million kilometres, when they are both on the same side of the Sun. But they're only in this position for a moment before the distance grows again, and the distance never remains constant. All the solar system planets are moving at different rates in their orbits around the Sun. Launching a spacecraft is like throwing a ball at a moving target from a moving vehicle, not an easy feat. Engineers must calculate the ideal time to make the jump on a circular path from Earth's orbit to where Jupiter will be when the spacecraft arrives, not where it is when the spacecraft leaves Earth. So assuming we have the most powerful launcher available and we launch on the shortest trajectory at the right time when the planets are aligned correctly, how long would it take? Early space missions such as the Voyager and Pioneer probes made the journey in less than 2 years, and the fastest any object has travelled to Jupiter was the New Horizons mission. Launched on 19th January 2006, New Horizons made its closest approach to Jupiter on 28th February 2007, taking a little over a year to reach the planet. However, all these missions continued onwards, receiving a boost from Jupiter, but none were captured by the orbit like JUICE will be. 3. We want to be captured by Jupiter's gravity, not boosted by it. To get into orbit around the huge planet, we need to lose some energy, but slamming on JUICE's brakes at Jupiter would require an enormous amount of fuel. Engineers need to control the spacecraft's mass, balancing the amount of fuel with the instruments it needs to carry to complete its mission. The more mass the spacecraft has, the more fuel it needs to carry, which increases its weight and makes it more difficult to launch from Earth. JUICE is one of the heaviest interplanetary probes ever launched, at just over 6,000 kilos, with the largest suite of scientific instruments ever flown to Jupiter. To get a spacecraft into orbit around another planet, we must match its orbital energy. When JUICE was launched, its orbital energy was the same as Earth's. It must gain energy to overcome the pull of the Sun's gravity, and will do so by stealing some orbital energy from Earth and Venus. Depending on the relative direction of motion of the planet and the spacecraft, a gravity assist can either speed up, slow down, or change the direction of the mission. The spacecraft also deflects the planet, but by such a minuscule amount as to be insignificant. Nonetheless, Newton's third law of motion has been preserved. To every action, there is an equal and opposite reaction. The world of orbital mechanics can be a counterintuitive place, but with a bit of patience and a lot of planning, it allows us to do a great deal of science with just a little fuel. So JUICE is taking the scenic route, using the gravity of other planets to carefully adjust its trajectory through space and ensure it arrives at Jupiter with precisely the right speed and direction. This incredibly complex, constantly evolving route has been carefully planned out by JUICE's dedicated mission analysis team over the last 20 years. Somewhat counterintuitively, using the lunar-Earth flyby to slow JUICE down at this point in its journey is actually more efficient than using the flyby to speed it up. If we had instead used this flyby to give JUICE a boost towards Mars, we would have had to wait a long time for the next planetary flyby. This first braking manoeuvre is a way of taking a shortcut through the inner solar system. JUICE come extremely close to both the Moon and Earth, meaning that real-time pinpoint accuracy is required in all navigation manoeuvres. During the flyby, operators keep a careful watch on the data coming down from JUICE, making any tiny adjustments needed to keep the spacecraft on the right course. Lunar-Earth flyby provides a prime test environment for instrument teams to collect and analyse data from a natural surface in space for the first time. For some instruments, this is the only opportunity to make certain measurements during JUICE's entire 8-year journey to Jupiter. It gives scientists and engineers the chance to calibrate their instruments, smooth out any remaining issues, and who knows, they may even make some surprising scientific discoveries. It will change JUICE's speed and direction to alter its course through space, but it's a daring feat. Thanks to this flyby, Earth bends JUICE's trajectory through space, braking it and redirecting it on course for a flyby of Venus in August 2025. From that moment on, the energy boost will begin, with JUICE being whizzed up by Venus and then twice by Earth. The space exploration equivalent of drinking 3 back-to-back espressos. Once JUICE arrives at Jupiter, it will get close to Jupiter's moons, trading energy with them that they've held onto for billions of years, to get a view of these environments like never before, helping us answer some questions such as, could there be life under the frozen oceans of Ganymede, Callisto or Europa? What can we learn about the formation of planets and moons throughout the universe? Through the wonder of flight dynamics, by trading energy with the universe, we will soonish find out.
This is SpaceTime. Still to come, 3 more Australian satellites sent into orbit. And later in the science report, a new study has found that tiny volcanic glass shards found in Tasmania actually originated in a volcanic supereruption in New Zealand. All that and more still to come on SpaceTime. Three more Australian satellites have been sent into orbit. This latest trio flew up aboard SpaceX's Transporter 11 mission aboard a Falcon 9 rocket from Space Launch Complex 4E at the Vandenberg Space Force Base in California. Transporter 11 is carrying 116 payload satellites, including CubeSats, microsats, and an orbital transfer vehicle carrying 8 payloads. The 3 Australian satellites on the manifest included the Waratah SID and Kuava 2 6-unit CubeSats and the Canyini microsatellite. They follow the arrival in orbit of Curtin University's Binar 2, 3 and 4 CubeSats, which are now aboard the International Space Station's Kibo module after flying up a few weeks earlier aboard the Cygnus NG-21 cargo ship. As for the new Aussie arrivals in orbit, well, the Waratah Seed Space Qualification mission was developed by the University of Sydney and is carrying a range of experimental technology demonstrators for 5 Australian space startups as well as several local commercial clients. The Australian Research Council's Kuava 2 CubeSat is equipped with a hyperspectral imager as well as a GPS reflectometry payload developed by the University of New South Wales for Earth observation and resource monitoring. Meanwhile, South Australia's Canyini spacecraft is also carrying a locally developed hyperspectral imager designed to analyse vegetation and soil compositions and detect smoke from bushfires. Other payloads aboard the Transporter 11 mission included the European Space Agency's Arctic Weather Satellite and the FISAT-2 CubeSat. ESA's Arctic Weather Satellite is a prototype mission. It aims to improve weather forecasting in the Arctic region, an area that currently lacks data for accurate short-term forecasts. It's equipped with a 19-channel cross-track scanning microwave radiometer, which will provide high-resolution humidity and temperature soundings of the atmosphere in all weather conditions. It's a forerunner for a potential constellation of similar satellites to be known as the EPS Sterner, designed to provide an almost constant stream of temperature and humidity data from every location on Earth. That will support research into climate change, which is occurring at a faster pace in the Arctic compared to other parts of the planet. As for FISAT-2, well, it's a CubeSat showcasing different artificial intelligence technologies designed for Earth observation. The probe's equipped with a multispectral camera and a computer running 6 different AI applications that analyze and process imagery while in orbit. The satellite's designed to turn images into maps, detect clouds in the images, classify them and provide insights into cloud distribution, detect and classify vessels, compress images on board and reconstruct them on the ground, reducing download time, spot anomalies in maritime ecosystems, and detect wildfires. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. A new study has shown that babies born to fathers of an older age may be more likely to have several health complications at birth. A report in the Journal of the American Medical Association looked at data from a decade of births across the United States totaling over 45 million in order to investigate the age of fathers and how that might impact on birth outcomes. The authors found that the proportion of babies being born in the United States to fathers over the age of 50 is growing, with these fathers more racially and educationally diverse than the general population. The authors say that after controlling for risk factors that come from the mother, having an older father was associated with a higher risk of preterm birth and lower birth weight. They also found that older fathers are more likely to use assisted reproductive technologies and also more likely to have female children. Korean scientists have developed bacteria that can produce rigid heat-stable plastics similar to PET and polystyrene. The findings, reported in the journal Trends in Biotechnology, could bring industry a step closer to replacing petroleum-based plastics. The authors engineered the bacteria specifically to produce and withstand the plastic in ring-shaped structures, which are usually toxic to microorganisms. While more research is still needed, the authors say the resulting product is biodegradable and has physical properties that could lend it to biomedical applications, including drug delivery. A new study has found that tiny volcanic glass shards found in Tasmanian wetland sediments could have originated from a supervolcanic eruption in New Zealand over 250,000 years ago. If confirmed, it's the first such example of this type of glass being identified in Australia. The findings, reported in the journal Quaternary Science Reviews, follows the discovery of silica-rich volcanic glass in 2.5-metre deep peat and river sediment from the Yellow Marsh district. The authors estimated its age using radiocarbon dating of plant spores and sediments above it, and then compared its chemistry to signatures of glass shards from various volcanic eruptions around the planet. The samples best match the Orowanui supereruption 256,000 years ago at the site of present-day Lake Taupo. The findings support modelling showing Orowanui ash may have reached Australia. From prehistoric times, long before language, humans have been using non-verbal cues for communication. The shaking of the head, the lifting of an eyebrow, a smile, these are all expressions that humans use to communicate. Nowadays, many studies and peer-reviewed research on nonverbal communication shows that a lot of nonverbal behaviour can be a sign of underlying emotional states. However, that doesn't mean that you can read a person confidently just by their body language. And that's the thing, so many experts have come out of the woodwork, each claiming to be proficient in body language reading. Tim Mendham from Australian Skeptics says psychologists agree that emotional states can find an outlet in body language. but there's just no complete scientific evidence for many of the claims being made by so-called body language experts.
Everyone uses body language to see how someone is reacting to you. If someone raises their eyebrows, it's in shock, etc., or hello, what's going on here? All sorts of things that people do in reaction, in communication with each other. People do it naturally. It's just part of the human condition. But other people are sort of saying it's more
autism, in which case you have no idea what they mean.
That's right. Yeah, that makes it very hard. It's everything about you. It's your arm movements. It's the way you stand, the way you have nervous tics or whatever, or just habits that you do when you're confronted with other people or in a difficult situation or even a non-difficult situation. It's when you try and make it a science. There are some people who have said that there are 20,000 facial expressions that people can have. I've got no idea how they measured 20,000.
Could it be that they make it up?
It probably is easy to make it up. This was someone in 1952 saying this, with a wonderful name of bird whistle. But, I mean, he said that, and he also said that 65% of face-to-face communication is done non-verbally. Others have said 7% is via what is said, 38% through tone and voice, and 55% is through body language. There's all sorts of figures thrown around. Some are still talking about fleeting expressions lasting as short as a 25th of a second. That's a short time. You have to be very, very quick to pick up on that. Others have said, obviously the face is the big thing because you can see a face, it's not normally covered. Others have suggested, no, the real seat of body language is the feet, and I think that's an interesting one to measure. You're talking to someone, their feet are under the desk, you really can't see them. But apparently, if you're shaking your feet, etc., you might be nervous. If you cross your legs or whatever, they're saying if they're interested, your feet are facing the speaker. If you're not interested, the feet are facing the door, which would be difficult if the door is behind you. All sorts of issues that have cropped up a lot.
I was always told handshakes are an important one too. When you shake someone's hand, as you shake their hand, if you move your wrist so that your palm is facing downwards, you're going to dominate that conversation.
In the same way as you have a two-handed shake, one hand and one on the forearm, it means you have control over them. You do the pull towards you handshake, that's also a dominant thing. And of course the old squeeze too hard. It's also just someone just being nasty and hurting your hand. That puts you off so they can then win over any argument. The problem is that as a science, it's very unreliable. Try and get some sort of reliable thing out of it. Using it to read people, apart from what you can normally do, which is someone's eye movements, etc.
It's like
gaze, aversion.
Using body language experts to work out who really won the debate, the presidential debate or something like that.
Yes, and I've seen, I get regular correspondence from a body language expert who looks at every video of a politician and then runs through what they did wrong, expressing themselves. A lot of it's exaggerated. A lot of it comes from 20,000 facial expressions or whatever. And that picking up and getting something empirical out of it, apart from the obvious things that everyone reacts to, everyone's aware of. It's not a pseudoscience as such, but it can be a bit of an over-exaggerated science, I think. It's the ability to actually do things. Some people put forward things you can do to express yourself. I don't know if that means fooling people. One is the concept of mirror neurons. When someone does something, you do it too. Spatial awareness, don't come too close to someone. Give them their body space. Posture, make sure your posture, regularly checking your posture, make sure you can sit upright, etc. And eye contact variability. Practice varying your eye contact. Don't always stare at someone in the face. Actually, most people don't. Most people do look away when they're talking to someone, and then they look back, and then they look away again. You know how off-putting it is with someone staring straight at you.
If you have autism, you never look someone in the face, and then then they think you're being deliberately
evasive.
Yeah,
evasive.
My philosophy is never look someone in the eye when you're eating a banana. That's Tim Mendham from Australian Skeptics. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.